So we're going to continue reviewing graphing of 3D surfaces. Let's take a look at this one. Again, you need to recognize that not all three of them are squared, so that has a determining factor to it. It is not a plus here, it's actually the minus, so you need to recognize it's the saddle guy. Okay, and here's how you can draw this guy. Look at traces. So the xz trace is z equals x squared. So, and it's a positive, and it's always hard to see these, but this green guy is coming in and out of the board. Okay, so I know it looks flat, but it's coming out of the board and into the board. And then the other guy is to see the yz trace, which is z equals negative y squared. So on the yz plane, which is the surface of this board, you have that, okay? And this is hard to see unless you maybe get your hands out and kind of create your own parabolas, but that's the saddle part, okay? You could kind of argue that the blue is hovering around the base of the horse, or the body of the horse, and then the green is kind of the saddle part that you get a hold on to, and the horse is trotting into the board or trotting away from the board. But that's kind of my perspective that I see right now is imagine the horse's body going directly through the blue part, and then the green is kind of where you're straddling it and holding on to the top of the green. Okay? So that is the saddle, which if you guys need to know the word for it, it's more than just a saddle. It's the hyperbolic paraboloid. Okay? Now, surfaces of revolution. So let's take a look at one like this. I love when it's z's and y's because it's very easy to draw that 2D graph. Because here's y and here's z. That's kind of like your y and x when you graph in 2D. So it's pretty easy to graph z equals square root of y. It is that. It's very similar to the same thing as y equals the square root of x. So you have points like 1, 1. You have a point over here that is 2, 4, and so on. And it spins around the y-axis, which means all of these points spin. Ooh, that was a little bit too big. Let me draw this a little bit better. Make them correspond with the correct radius. And so it should look like that. That's that parabolic bowl, okay? And technical term, it's the elliptical paraboloid. This is an elliptical paraboloid. So I'm going to show you how to get that equation by using the surfaces of revolution. The whole thing is, since it spun around the y, the formula is, when you spin around the y, guaranteed x squared plus z squared. These are circles. And if you look at all those green guys that I drew, they're all circles in terms of x and z. Because stare at it from the right side of the board here where you're just looking at the x and z plane. Don't worry about the y's. Smash all of those rings down onto the xz, and they are circles. And those circles are completely dependent on the radius. And that radius I want in terms of an r squared. Okay? And that r squared in this case, let me be a little bit more specific. X squared plus z squared equals r squared, but r is in terms of who? Which variable is it in terms of? It's in terms of y. So x squared plus z squared equals some radius function in terms of y. Well, do you already have that radius function? Yes. So you can throw that right into there, and you would have x squared plus z squared equals square root of y squared. And this simplifies to x squared plus z squared equals y. And if you look back in your notes, that is the formula for an elliptical paraboloid that is circled around the y-axis. Okay. Let's look at another one. I think I have another one about spinning. Okay, this one's spinning on the x-axis. So let's take a look at the x-axis spin. So graphing wise, it's a little bit harder to see because it's going to be all in the xz plane. Let's see, what can I do here? What could I do here? What is 4 minus x squared, just in general? What shape is that back in geometry, back in pre-calc? What shape is that? Okay, this here is a circle, or I guess I should say half circle, centered at origin with radius equals 2. Okay, so it's centered at the origin with radius equals 2. But then, if I wanted to graph this, I might want to divide by 2, both sides. So let's kind of see what I get. Let's plot some points. If I plug in 0, I get 4 minus 0 is 4, square root of 4 is 2, divided by 2 is 1. Okay. Another nice guy to plug in is 2. Let's see what I get. Plug in 2, and I get 4 minus 4 is 0, square root of 0 is 0, divided by 2 is 2. So what it looks like it happens is it looks like it becomes the half circle, but it's scrunched down. Because normally it would be up to 2, but it got scrunched down by the divide by 2. Okay, so I have that shape there. And when it's spinned on the x, that means circling things gives me circles all along the x-axis. Okay, so to me this looks like a football. Okay, which is an ellipsoid. Okay, so when I do that, I would have, let's see, spinning around the x gives me y squared plus z squared equals some sort of function about r of x squared. Now y squared plus z squared equals, again, luckily I have it, especially since I divided by 2, I have it right here. That would be 4 minus x squared all over 2 squared. That simplifies to y squared plus z squared equals 4 minus x squared all over 4. Okay? And if you want to see why I called it an ellipsoid, this simplifies to y squared plus z squared plus x squared over 4 equals 1. So trace-wise, the yz, those traces as circles, which we already said. The zx's are ellipses. And the y, what one am I missing? Y-x's are also ellipses. Okay. I didn't say on this one that it needs to be the red graph above the z or above the x-axis. So technically this guy does go down and down. I would have needed to really specify because this would also give me some circles flipping, and it would almost turn into like a candy cane where you have the football part and then you have the tails of it. So I'll be more careful when I specify which part you're going to be spinning. I just wanted the top part in this case, so that's my fault. I think I got a couple more just because I want to make sure you guys understand these. So take a look at this one. Again, this is a z and a y, which is really nice because it's easy to draw on the board because the board itself is the zy plane. z equals 8y. Mentally think algebra and say y equals 8x. So that's a pretty steep line right there. And it also goes down. Okay, if you wanted to plot a point, you could say over at 1, it goes all the way up to 8. Okay, so you have that. Spin around the z. So that means circles hover around the z-axis. And this way as well. So hopefully you see there, that is the cone. And the verbiage for the word cone is, again, the elliptic cone. Okay. So now with that, circles around the z gives me x squared plus y squared is a function, a radius function of z squared. Okay, so right now I have z equals 8y. I need it in terms of z. So we're not there yet because I need it in terms of z. So we need to solve for z. So if I have that, you might want to come down here and say, okay, that means y equals z over 8. Now I can throw that in. So I have x squared plus y squared equals z over 8 squared. X squared plus y squared equals z squared over 64. And to get it in the form we're used to, x squared plus y squared minus z squared over 64 equals 0. And remember, this is the cone, not the hyperbola of one sheet, because yes, there's one negative, but that is a 0, not 1. If it was the 1, it would be the one-sheeter. But since it's a 0, that means at the origin, that belt radius gets completely pinched down to nothing, which just gives you the dot there. Okay? Let's look at, so those are the reviews of all of the graphs. Okay? So it was kind of 2 video lectures. One was 20 minutes and one was 12 minutes. I'm going to start, even though I have more time on this one, I'm going to stop it and then just start completely fresh with the new notes on 11.7. So you kind of have some split videos where some of it's all review on surfaces of revolution, and then the other part is going to be the new material for today's lecture.